Good afternoon, everyone. My name is Rachel Harris, and I'm a fifth-year PhD student in chemistry here at Northwestern. Today, I'm going to take you on a little adventure down to the nanoscale, where you'll learn about tiny rocks with some big possibilities. So I work in the field of nanotechnology, and I think that most people have some idea that nano means small, or that it means miniaturization. But what I want to do is just illustrate how small is small and what does nano really mean. And so to do that, I want you to imagine an eyelash the size of the Hancock Tower in downtown Chicago. If you have an eyelash that's the size of a skyscraper, 1 nanometer would be about the thickness of a dime on the sidewalk, and a nanoparticle would be the size of a pea. That's really tiny. And as you'll see in just a second, the nanoscale is really interesting for us to study because this scale affects a material's properties. So what I'm showing you here are 3 versions of the exact same material, lead sulfide. And you can start on the atomic scale where you have just an atom of lead and an atom of sulfur, and they alternate together to form a crystal. Now, if you have a few thousand lead and sulfur atoms, now you're on the nanoscale. And this clump of atoms, if you look at it in a really powerful microscope, you'll see that it looks like dots. And because scientists always choose the most boring name possible for literally everything, we call them quantum dots. A vial of quantum dots of lead sulfide looks like a brown suspension. These particles are so small that you can dissolve them in a liquid. And this contrasts really clearly with macroscale lead sulfide, the scale that you or I would be able to pick up a chunk of lead sulfide from the ground, and that geologists call the mineral galena. Now it should be really obvious that galena lead sulfide is a shiny gray rock, and it has incredibly different properties from this brown suspension of particles. But as you'll see in a second, that's just the tip of the iceberg, because even within the nanoscale, size affects properties. And with quantum dots, we see this most clearly with color. So these quantum dots are all made of the exact same chemical material, but they're different sizes. So the smallest quantum dots glow blue, and the largest quantum dots glow red. And this relationship between size and color makes quantum dots really attractive for a number of applications. Like bioimaging, where scientists can use green and red glowing quantum dots to look at cells in much greater detail than they could with a traditional stain. Security. Counterfeiting costs the world economy $500 billion a year. And you can create security inks using quantum dots to print on money and make them harder to duplicate. Solar power. Quantum dots are fantastic light absorbers, and they're also really great at taking energy from the sun and converting into electricity that we can use to power our daily lives. Finally, displays. Because quantum dots are so small and so brightly colored, you can use them to create displays that are higher resolution and with a wider range of colors than you can using a traditional LCD. Now, if you want to use quantum dots to do all of these great things, you need to understand the chemistry of the surface, and I'll tell you why. Imagine you're eating a bowl of your favorite cereal, and as you know, one thing always leads to another, and suddenly you're on bowl 4 or 5, right? So I can guarantee you that the last bowl of cereal from that box will always taste better than the first one, because when you get down to the end of a box of cereal, you're left with these tiny particles of cereal dust. And the reason these tiny particles taste so good is because you have a greater surface area that's reaching your taste buds. Now, a quantum dot is much smaller than a particle of cereal dust. They're so small that they're almost entirely surface, and that's what makes understanding the surface chemistry so important. Now, when we make quantum dots, they're covered in these long, greasy, insulating molecules. And that's a problem, because if you want to put quantum dots in a TV or in a solar cell, they need to be able to conduct electricity, and if they're covered in grease, they're not very conductive. So people didn't realize this at first because in a microscope, a quantum dot looks kind of like this. It just looks like a dot. But we now know that in real life, a quantum dot looks more like this. So my research involves understanding how we can optimize the chemistry at the very edges of this koosh ball so that we can make quantum dots more viable for incorporation into new technologies. One of the ways that we do this is by using surface chemistry to change quantum dot color. Before, I showed you a slide where the size of the quantum dot changed the color, but now we can also do that by just changing the chemistry of the surface. So these quantum dots are all the same material, they're all the same size, but I've gradually replaced these long, greasy, insulating molecules with a new molecule that we think will make quantum dots work better. So they start out clear because they're absorbing invisible light, and they shift gradually to absorb visible light, so they appear yellow to our eye. So, in conclusion, understanding and optimizing the surface chemistry of quantum dots is crucial to their incorporation into new and exciting technologies. Using surface chemistry, we can make quantum dots more biocompatible so that we can image this mouse without causing it harm. We can make them brighter and more luminescent for better display technologies. And we can make them more conductive to incorporate into solar cells and other electronic devices to power a brighter future. Thank you.